Hello, everybody. I'm pleased to talk to you today about the college's climate action plan. Today, we'll talk about what we have done to translate that strategic plan into a design and a implementation plan. I'd like to update folks on the goals for the project. You'll remember we set the goal of achieving carbon neutrality by 2030. And there were a number of elements to this. We wanted to absolutely minimize the on-site emissions that we created from burning fossil fuel and maximize the use of renewable electricity. We strive to create true decarbonization with minimal reliance on carbon offsets. To do so, we're going to implement cost-effective and forward-leaning technologies that represent state-of-the-art. This meshes well with the state of the college's current infrastructure that dates back generations. Will be able to replace aging and archaic systems with modern, efficient systems that are consistent with current practices. In order to achieve decarbonization, there's a number of steps that we'll take and a number of technologies that we will use. First and foremost, we'll have to maximize the energy efficiency of our current buildings and then convert the legacy-based steam system, which is very inefficient means of heat transfer, to a modern low-temperature hot water heating system that transfers energy without the inherent inefficiencies. We will be electrifying the heating and cooling systems through an implementation of ground-sourced heat pumps and air-sourced heat pumps. These will combine with the central cooling systems and eliminate antiquated steam-based absorption chillers. We'll also be purchasing or generating virtually all of the electrical from renewable sources. And should it be necessary, if there are residual emissions, we will purchase a minimal amount of carbon offsets. At the heart of this transformed infrastructure are ground-sourced heat pumps powered by renewable electricity. Heat pumps will replace conventional boilers as a means to generate energy. You may be familiar with heat pumps from residential applications, but heat pumps are a means to transfer heat. They extract or reject heat from the earth, raise or lower its temperature, and then transfer that energy through a piping network to our buildings. The benefit of heat pumps is that they can run in either directions to either heat or cool, and they can also be configured so that they can make use of the energy in our buildings to reject heat to a building or extract heat from a building. This is reflected in the thermal profile for the college, which over the course of the year shows some seasons, mostly in red, are primarily heating, and some seasons are primarily cooling. But the purple at the center of this, around the axis, reflects periods of the year when the college is both simultaneously heating some buildings and cooling some buildings. And this is the point at which the heat pumps can be used to extract that energy and exchange that energy for beneficial use. Another key element of the transformed infrastructure is that the heat pumps are capable of being powered by electricity. For the electricity, we will make use of renewable energy. As you may know, we are entering into a power purchase agreement currently for electric purchase in 2022. We may be able to expand these type of arrangements for sourcing of power. The other option will be to consider on-site renewables through photovoltaics installed on some of the college's land holdings. As I noted earlier, carbon offsets are not a major component of the college's climate action plan. They will only be used in minimal quantities to offset residual emissions that may occur when the college has to heat the campus utilizing backup boilers during situations in which resiliency is critical. At this point, I'd like to ask Tom Davies to walk us through some of the design features of this transformed infrastructure.
Really excited to be able to present this to everyone. The schematic design is before you now. very generally speaking, we will have a large geothermal well field that feeds into a new energy center that will house both ground source heat pump systems as well as air source heat pump systems that will then feed both a hot water and cold water network of underground piping that feeds the rest of the campus. Our existing central plant will be converted to provide peak load heating and cooling, as well as backup heating and cooling for power outage situations. You see that here toward the top center of the diagram. And we'll go into each of these elements in more detail. As Jim mentioned, we're shifting to a low temperature hot water system. By reducing the temperature of the heating transfer from the central plant to the buildings, a whole series of efficiencies are possible. And we are also able to employ various technologies. This diagram shows that as you get into lower temperature hot water, the efficiency increases. So that's actually shown here in the heat losses, in the blue line shown as inefficiency. But of course, the lower the temperature, the higher the costs as well for all the conversions of the existing buildings, which we have many of. So we had to work with our engineers to determine various scenarios and model them out before we determined what the ideal range for our system would be, which is between 130 and 140 degrees. The ground source is reliant on heat exchangers that are drilled into the earth, and the design really relies upon the specific geology that we have present here on our campus. In order to determine this, we installed a test bore at 800 feet of depth, tested that with a test rig to determine the amount of heat transfer, the rate of heat transfer, and the amount of groundwater present on our site, all of which checked out quite well, and those data could be incorporated into the design. The location for our geofields will be in the athletics fields at the south end of the main campus. The amount that we are anticipating is in the 4-acre range, perhaps 5-acre range. And as you can see here, that can easily be accommodated in the current soccer fields or soccer fields plus some part of the outfield of the baseball field. You'll note in these red outlines that we are avoiding some areas that could in the future potentially be campus building sites to make sure that we're not precluding anything that might want to come along in the near or distant future. The installation will be phased, and I'll show you that in a few more slides so that we can dial in exactly how much is necessary with empirical testing of the first phases. As I mentioned earlier, the geofields will connect into the new energy center. A number of locations were studied for that siting, and one of which we thought a little bit about at the student center site. However, there are a number of reasons that doesn't really work from a campus planning perspective, most notably that there will be some sound associated with this plant, and it was desirable to move that to the periphery. Campus planning also emphasizes the desirability of preserving as much land as possible toward the core of the campus. And there is really not a significant penalty relative to cost or engineering for the new energy center to be located at the periphery. So as you can see here, recommended site is to the southeast in a portion of what is now a parking lot. The specifics of that site are to be determined as we move forward with the design phase. Of course, resiliency and backup power is critical, particularly as we head into a future in which we are braced for the potential of longer outages. Our system is conceptualized to include full resiliency backup provided in a number of different ways. Of course, with an electric-based system, the amount of electricity generation that would be required to run those heat pumps on a cold day would be tremendous and is not feasible. And so As you can see here, the heating resiliency is provided through new natural gas or biofueled boilers that will be located in the existing central plant building. We're also expanding our electrical capacity to be able to run the entire system, not the heat pumps, but the rest of the system, and provide both heating and cooling to the campus for extended periods. Moving into phasing, of course, this is a very significant project and even cut up into 4 or 5 really phases. Each of those phases is quite significant. Phase 1A is what you see before you here. This will leverage the newer or current construction projects that are largely already set up to run on low temperature hot water, including the Greenway dormitories, the new science center, and the student center and dining commons that is now in design. A few other buildings will receive some modifications so that they can operate on low temperature hot water, including Fairweather, Benesky, the Mead Museum, and Whelan and King. This will all be fed from a steam to low temperature hot water heat exchanger that will be located in the existing boiler plant. So the source for the heating will still be fossil fuel based from our current boiler systems, but will benefit from the efficiency of distributing low temperature hot water versus steam for these buildings. The amount of heat lost through the pipes associated with low temperature hot water is significantly less than that associated with steam. This work will be completed in 2022 and lead directly into phase 1B. Phase 1B introduces the new energy center that you see to the bottom right, and the first phase of the geo wells, roughly located as shown here in soccer fields, and will introduce a new network of distribution piping that loops the core of the campus. At that point, the buildings that are in the darker tone here will be picked up onto that new system. That is, as this says, more than 50% of the campus will be on the system at that point. Phase 2 then expands to the north of the core campus and expands also the GeoWells associated with that. By doing this in a phased approach, we can, again, learn empirically as the performance of the GeoWells and the sizing of the second and third phases can be dialed in for efficiency. Phase 3 then looks to the athletic complex and buildings in that area to the southwest corner of the campus. And that takes us to 2030, when we can very ceremoniously turn off our antiquated steam system and feed the entire campus off of the new energy center at the southeast of the campus. Phase 4 then looks to the periphery, both north of College Street and west of South Pleasant Street, and potentially expands the central system across the roads to pick up these buildings. As noted here, this is optional. This scope could happen sooner, it could happen later. Those buildings are currently standalone. They have their own heating and cooling systems, and the college can determine whether they will be picked up on the central system many years from now. We don't need to make that decision for quite some time. So pulling it all together, here's an overview of the phasing with the different pieces, and then the costs associated with this. Of course, we break down the costs into each of the phases. These costs are escalated, and you can see that the number to the bottom right is $113 million, is dollars that are current at that time. You can see that a significant chunk of that is related to phase 4, $20.5 million. And we'll circle back to that in a moment, because of course, the next thing we did was look at options to reduce the cost. The first option was to delay that decision about phase 4, the non-core campus. And this is really the heart of the logic here, is that it is worth 13% of the total area, but only 5% of the greenhouse gas emissions associated. So in terms of bang for the buck, it's quite a bit of money for that amount of greenhouse gases. The second thought with postponing of that periphery is that technology is advancing rapidly in this arena. And it is entirely possible that in 5 years, when the college needs to make this decision, there will be newer, better, more cost-effective solutions that could be applied to those buildings. Alternative 2, we've deemed the Carlton model, because this is how they proceeded with their older buildings. separates the heating loop into two sections, a low temperature hot water area and a high temperature hot water area. By doing this, we can deliver higher temperature hot water to the older buildings during the winter months and postpone the considerable amount of building system renovation and replacement until such a time as there would be renovations to those buildings due to a programmatic change or end of useful life. So this enables us to do less intensive building conversion immediately and spread some of that out over the longer term. Alternative 3 is the idea of combining both alternate 1 and alternate 2. The costs associated with this are significantly reduced, as you can see here, an escalated cost of $82 million. And this is the recommended direction that we enter into this next phase of the project with. With that, I'll hand it back to Jim to continue with the conversation about the finances and other aspects of the project.
Thanks, Tom, for walking us through the details of the design. I thought I would touch on the project's cost and its financial paybacks. It's important to consider this project not just a capital cost, but also to recognize that as a result of the inherent efficiencies of this new infrastructure, there will be considerable savings on energy costs, as well as avoidance of capital costs for our existing legacy system that was installed generations ago. The slide I have in front of you that represents net present value of life cycle cost illustrates this point very clearly. If we were to continue business as usual and to reinvest in our existing plant and continue to burn energy at high rates, we would have a net present value of $225 million as measured through 2050. We can contrast this to the options that we have put forth. Represented in the third column is alternative 3. And we can see that while the capital cost is higher than the business as usual, the energy cost is considerably less, as are operations and maintenance. To underscore the fact that this project is not just a cost, we have done a break-even analysis taking into account debt issuance to finance the project. And it demonstrates that we see a break-even point after the system is fully implemented somewhere around the 2045 range. I'd also like to focus on the greenhouse gas impact of the proposed alternate number 3. You can see from the graph on the left that as we hit 2030, there is a substantial reduction in greenhouse gas from what the business as usual amount is currently, which is 17,500 metric tons per year. With the implementation of these phases at 2030, we reduce our emissions to about 2,500 metric tons of carbon. It will be necessary potentially to offset that residual amount with carbon offsets. Alternatively, we may be able to burn biofuels, which could arguably reduce this even further. The graph on the right represents how that carbon is reduced. And it is as a result of energy conservation measures in buildings, the inherent efficiencies of the low temperature hot water for transferring heat, and then the emissions reduced by replacing grid purchase electricity with renewables. As Tom noted earlier, we are now in the phase 1A design process. We're using a notable firm called MEP Associates, who have a practice that is noted for their work on energy system transformations. They have been just excellent to work with, and they are now working collaboratively with us on phase 1A design, which will conclude with construction documents at the end of this calendar year and set the stage nicely for construction to take place during the summer of 22, when we'll be establishing that low temperature hot water piping network on the eastern side of the campus. The cost commitment through The end of that design phase is roughly $1.6 million. And we will also be doing some design on the central power plant that will house the heat pumps. We look forward to seeing you at the upcoming meeting, at which point we'll be able to address any questions or comments you have about the design we have shared with you today. And thank you for your time.